Hello, welcome back. This is our last section. This is Dr. Kellogg, and you have been working your way through the last couple chapters of MGF 1106, Liberal Arts Math, and since we had to go online, we had to change how we delivered the content. Much rather see you face-to-face, but this is what we have, so we're going to make do, right? I just noticed that I've got to clean this up a little bit. I had a recording that didn't work. I don't know what happened, but I had to start over again. So 12.5, last section. We are finishing up, and then we'll have a test in a couple weeks. I emailed you a very important sheet of paper called a Z-score that you'll need for this section. We'll talk more about that as we get going. Last week we talked about measures of dispersion, range, and standard deviation, right? And those numbers were used to kind of describe how close the data set was. Was it tight together, a low standard deviation, or was the data spread out, a large standard deviation? And that's what that tells you. All right, remember that. Now we're going to take a look at something called the normal curve. The normal curve. And if you kind of think about what we've been doing in this chapter, as we worked our way through kind of what you do with a data set, right? First you design your survey and you figure out your sample size, and then you organize the results. You get the data, and then you figure out what are the best ways to display the data. Maybe a pie graph, maybe a bar graph, maybe a histogram, maybe a stem and leaf plot. And then you start measuring the data. What are the different measures of central tendency? The mean, the median, the mode, the mid-range. Measures of average, they all start with M, measures of central tendency. And then last week we took a look at range and standard deviation, which is a measure of how dispersed the data is. Well, lastly, we take a look at a graph and graphs involving the data set and information that talks about how we can start to make predictions and rank items, rank data within the set, which is what everybody's interested in, right? Don't tell me what I got on my test. I want to know what everybody else got too. I want to know if I did better than everybody else. That's why you get something called your percentile rank when you get your SAT tests. We'll talk more about that. So normal distributions are the key to this section. And what we find out is when you start working with data, certain data sets, if your survey and your gathering tools are designed correctly, can produce data sets that have some really, really valuable mathematical properties. Now, these are data sets that are not biased, they're not influenced by personal opinion. Things like shoe sizes, heights, weights, IQs, lifespans of light bulbs, how long your tires last, how likely are you to get in an accident. These things occur within the scope of life, right? You can't change your shoe size or your height, so you can't bias something like that, all right? So studies that take a look at those type of data will tend to be what we say normally distributed. And if you graphed them, and we've looked at some of these graphs, they would tend to look like this. This is an example of women's heights. Now this would definitely be normally distributed, meaning can't bias it, can't influence it. It is what it is. And the larger your data set, the better it takes on the more it exhibits a normal distribution, which means most of the data will be grouped around the mean, and the larger your data set, the more balanced it tends to become. Look how balanced that is. Left side, right side, to where if you could actually do the population, like every woman, you'd get this beautiful shaped curve, okay? It's called a bell curve, and the data is perfectly balanced on either side of the mean, okay? But it's often impossible to do populations. It'd be very expensive and almost you'd be talking about 100 million people, right? So we tend to look at sample sizes, and we want to have a good sample. I want to make sure that if I'm going to do 100, I want my 100 to be well representative of the population. Maybe vary where I select the women or the ones that I interview. I want it to be kind of random, right? So that everybody has a chance to be picked and selected. But we won't talk a lot about that. So when you have a normal distribution, here are some of the properties. All right, it exhibits, its shape is called a normal curve or a bell-shaped curve. And that's what the back up here, right? This is called a bell-shaped curve. Right there, bell-shaped curve. Okay? This is interesting. Number 2, the mean, the median, and the mode are all located at the center of the distribution, or they're very, very close. They're either the same number or they're very, very close, meaning they're all located like right here. All 3 of them. Okay, pretty cool. It only has one mode, and it's symmetrical. It's balanced. It's got the same data above as it does below the mean. It's symmetrical. This picture right here, the left half and the right half are the same. If I fold the paper on the mean, then it will match up. That's symmetrical, right? Okay. Now that doesn't mean that every normal distribution is exactly the same. These 3 are normal distributions, 1, 2, and 3, but they're obviously different. Yes, they have the same mean, they're the same height, but number 1 is much tighter together and number 3 is much more spread out. Well, that just means that they have a different range, or probably more likely they have a different standard deviation. Right? The larger the standard deviation, the more spread out the data is. So which distribution, 1, 2, or 3, do you think has a larger standard deviation? Number 3, right. And which one has the smallest? Number 1, right, exactly. So that's what that looks like in a picture. Okay? Now again, I told you that researchers and statisticians get excited when their data exhibits normal distribution properties, because there are some mathematics that are very, very nice on these distributions. You can start to see just the balance of this. We're going to use terminology in this section. We're going to talk about the area or the percentage or the amount of the data set. Okay? So I want you to think about like this chunk as having more area than this chunk down here. Okay? The more area, the more people, the more heights, the more shoe sizes that are in these larger chunks. Okay? And this negative, this is on a normal distribution, the standard, the mean is your beginning, or it's the 0 locator, ground 0. If I go up 1 standard deviation, then I'm going to have a certain percentage of the data set or a certain area of the data set. And as I keep going up, all right, these pieces drop in size because I'm actually running out of people, right? I've got most of them. They're already right here. So obviously as I work my way away from the center, the mean, I'm going to have less and less of whatever, light bulbs, shoe sizes, heights, IQs, okay? But take notice that if you go 3 standard deviations below and 3 standard deviations above, you've got just about the entire data set. Notice there's some room down here in the tails. There's a little bit of room for a few more people, okay, but not much. This is just about all of it. Just about all of it, okay? Matter of fact, we're going to take a look at some percents here in a minute. So in a normal distribution, the bottom half, okay, the bottom half contains 50% of the data, and the upper half contains 50%. We normally don't go past 3 standard deviations because there's just almost nothing up here and almost nothing down here. But there's always a little bit Always a chance for a new world record. Smallest shoe, largest foot. Smallest foot, whatever you want to say. Okay? Lightest baby, heaviest baby. Always a chance for a new record. So there's 50% above and 50% below. Okay? Let's look at this a little more closely. And there's something called the empirical rule, which actually tells you how the data will fall very close to these numbers if you have a normal distribution. And it says that you're going to have about 68% within one standard deviation, plus or minus. If I go another standard deviation up and down, I'm going to have 95% of the data. And if I go one more standard deviation, 3 standard deviations, I'm going to have just about everybody. Just about everybody. So what does that look like? Well, it looks like this. Okay? So again, if I have a normal distribution, this is how I can expect the data to fall out. 34% in the first standard deviation, below the mean, and 34% above. Notice how that adds up to what? What's 34 plus 34? 68. Right. So I can make predictions about how many people, on the SAT will fall in here, or how many people's IQ will fall in here. Those are things that are normally distributed. Pretty cool. I can start to make predictions about how many male drivers, 18 to 25, will be in an accident if they drive more than 10 miles to work. Things like that. They have all kinds of data on things like that. Notice if I keep going, if I go another standard deviation, 2 below and 2 above, okay, I add 13.5, which is 27. Add that to 68, and what do you get? You get 95. So if I go 2 standard deviations below and 2 standard deviations above, I have 95% of whatever I'm studying. That's just about everybody. Okay? And if I go a little bit more, notice I pick up 2.35% and 2.35%, which is what? 4.7. Okay? Add that to 95, and there's your 99.7. I kind of ran out of room down here. 99.7. 3 standard deviations. Normally you don't go much beyond that because you've already got just about everybody. 99.7%. Okay? Now, this is great, but this is only good if the data is actually falling like right on these standard deviations. Then I can make predictions about things. Or if it falls right in the middle, because I can divide 34 into 2 and get 17 and, things like that. But even that wouldn't be right because this part right here, this half is more than this half. Okay? So this has limits to its value. Okay? But it is quite interesting, and it gives you an idea of where the data tends to fall. But to account for any data point, no matter where it falls in here, okay, we need another tool. Okay, and that's what this slide says. Okay, it says if the data falls right on those standard deviations, then this rule is great, but it often doesn't. So we need another tool. Okay, and that, my friends, is called the Z-score. Think of the Z-score as a measure of position. Every data item has a Z-score. Every data item has a Z-score, okay, which will rank it in the data set. It'll tell you where it falls. Your SAT score, things like that. Okay, your height, your IQ. They have a Z-score, which will rank it among the population. Okay? Now you can obviously have this formula written down, but it's really simple. Take the data item, subtract the mean, and be careful with your parentheses and your calculator and all that. Okay? Divide by the standard deviation, and you've got a Z-score. That's pretty easy, right? So data item, so data minus the mean divided by standard deviation. Okay? And there is a Z-score table. Okay? In your book, you'll notice it's on page... It's actually on 2 pages, 772 and 773. Okay, it's called Table 12.8. This is what I emailed you. You can print it out. You can use it. Don't write all over it though, because it'll mess you up. Try to keep it clean, or use small marks with pencils, but you don't want to get it all marked up. Okay. But you can use this for your homework. Keep it handy. Make 2 copies. Use it for your test. But it's how we look up z-scores. And I'm going to pause right now, and we're going to start the next video. When we come back, we will investigate how we use z-scores, and we'll build from here. Okay? All right, see you in a minute.